here, optimization, okay? We are going to be maximizing and minimizing functions. So if we have a function that we've defined, and the first derivative is has some zeros, it tells us what? Those are possible extrema. Do we know if they're maximum or minimum? No. We can use the sign chart on the first derivative. So if the first derivative increases, is positive on one side and negative on the other, we would know we had a maximum. And if it's negative and then positive, we know we have a minimum. Or we can use the second derivative test. So if I have zeros of the first derivative, these are possible extrema, otherwise known as critical numbers of the function, and I find my second derivative, and I find that those zeros of the first derivative make the second derivative positive, what's the graph doing? The original function. Second derivative is positive. And I know it's positive because I put the zero of the first derivative into the second derivative, and the second derivative is positive. That means that that zero I put in of here is not just a possible extrema, it is a, so if this is positive, that zero indicates where the function has a what? The minimum. Okay, this is all we have to do. Yeah, I say that as if this is all we have to do. Okay, now, what we have to do, and there's one in your homework, and it was, I worked with Zach on it, it was the Norman window one. Remember that one? Have you seen it? Have you started that homework? Okay, a Norman window is kind of an interesting thing. Zach, describe it for us. What's a Norman window?
It's a rectangle with a half circle on top of it.
Okay, with a half circle on top of it. Well, let's see if I can get that half circle to go over there. Okay, with a half circle on top of it. Now, it's asking you to do what? So I'm going to continue working with Zach because I know he and I were working on it. The problem ultimately is asking you to what?
Find an area.
Ooh. I can just find area, that's easy enough. But it's something more to it than just finding area.
Find, I don't know.
Yeah, you do. What's the problem saying? It's not just saying find area.
Find the maximum.
See, if I just want to find area, does that take algebra? Excuse me, does that take calculus just to find the area of this? No. Finding the area of this is back in, oh goodness, upper elementary. Isn't that where you find, you know, the formula for a rectangle and the formula for a circle? So finding area is no big deal, so to speak. But finding maximum area,
yeah,
that takes a little more than just finding the area of this. Because if I need to find the area, what information do I need? I want to find the area of this. I need what dimensions? Yeah, I need some information, don't I? I need to know the width and the height of this. If this is a semicircle, then this portion of it would be the radius of that circle. So we know how to find area. But the problem is to find maximum area takes our calculus. And that is what this section is all about. We're going to optimize, meaning we're going to find minimums and maximums. Now, is that really new information to us? We've been talking about that, haven't we, for this whole chapter? Finding where the graph has a minimum, where it has a maximum. So let's just go down, and please don't write this down. If you want to know this, it's in the book. Guidelines. Identify all given quantities. All quantities we determine, if possible, make a sketch. We have a sketch. We know what a normal window is. Write a primary education for the equation for the quantity that is to be maximized or minimized. on this one, what is my primary equation? Oh, by the way, it gives some other information, doesn't it? What else does it tell us, Zach?
That the perimeter equals 26.
What?
Uh,
Feet?
sure.
Inches?
Does it matter?
That's the builder of the house, you know. Yeah, probably feet, right? If you're going to have, you know, buy lumber, you're probably going to have a big window in this house and all that. Okay, so we're given the perimeter is 26 feet. But what is the primary equation? The perimeter equation? Y area. Yeah, absolutely. That's what you're trying to locate. So the primary equation is going to be the area equation for us. Let's go back and see what else we have here. So we got that now. Now we haven't written we don't have it written down yet, but we know what we're going to go for. Reduce the primary equation to one having a single independent variable. This may involve the use of a secondary equation. If I'm going to write area here, the area of this whole window, I'm going to have to involve y and x in that area. Do you see that? Area of this is going to be x times y. Area of this is going to be pi r squared, but half of that, so half of pi r squared. R, the radius is x divided by 2 because it's half of that window there, or half of that base there. So I have now my area equation in my head. Area is going to be the area of the rectangle plus the area of the semicircle. But when I do that, I'm going to involve a y and an x, which I really don't want to do. So that's what it's saying. Use a secondary equation so that you end up with a single independent variable in your primary. Single independent variable. So over here, do I want to write this in terms of, do I want a of x or do I want a of y? What's going to be my primary, my single independent variable? Well, you may not know that until you get into the problem. But the fact that I've got two measures in terms of x, I got the area of the semicircle in terms of x, and I got the area of this with an x in it, I probably am going to use x as my single independent variable. Now, you can disagree with me on that, and that's great. We should get the same answer either way. But I'm probably going to go with this. So I'm going to have to write perimeter. Now, what's perimeter? Distance around, right? Now, the assumption of this, and we got the right answer, so we're going to go with our assumption. The assumption is that we're not going to find out how much wood it's going to take to build that whole thing. The assumption is we want to find what this is, because this is not a piece in our, somehow they're able to, you know, cut the piece of glass without having to divide it up, which would be a very nice window. So it's just going to be the actual outside, not this piece in here. So how am I going to find the perimeter? Yeah. 2 y's, right? Plus an x. What's the perimeter of this going to be? Give you a hint, it's a semicircle. Because we're looking at half the circumference. The circumference is 2 pi r, so half that would be pi r. Yeah. R, remember, is expressed as x divided by 2. So my perimeter has a lot of x's in it, and it's got just these are going to be y. Do you think you could maybe solve the perimeter for y? Get an expression, put that into the y that you're going to get for the area, and then make it all x's. Are you following my logic? You will if you've thought through this problem a little bit, or, you know, and I'm not trying to give you the answer. Okay? That'd be cheating you out of the opportunity to work this on your own. I just want to help you see that it's not beyond your ability. Now, what we found as we worked through that you know, you don't always have nice, easy numbers. You got to use some arithmetic properly. Okay, determine the feasible domain of the primary equation. Well, if I come up with this area here and I somehow take its derivative and I then find critical numbers of my area by finding zeros of my derivative, and I get a positive and a negative, is that in my feasible domain? My critical numbers are going to be in terms of what? Critical numbers are going to be values for what? A, X, Y, or P? So could X be negative? Wouldn't make any sense, okay? So we've got to think about the reasonableness of our answers. Does it make sense? And then determine the desired maximum and minimum value by calculus. So what we end up with then is a very nice little problem that the hardest part's going to be writing these equations maybe, because the easy part's going to be taking the derivatives. You're really good at that, but sometimes you forget some of the other math we know. Okay, so this is one of those problems you're going to encounter. Got the idea? Break it up into pieces. Find the pieces that you need, add them together. Okay, well, let's see here. Maybe in the work we do today, we can come up with some other hints that will help you with some of those problems. Dairy farmer plans to enclose a rectangular pasture adjacent to a river. Stop right there. Can you draw a picture of this? Don't go any farther. Draw a picture. What's that going to look like? Okay? Can't get out there to see what you're doing. I'll get out there and see in just a minute here. My picture would look probably something like that. Here's my river. There's my rectangular pasture. Okay? To provide enough grass for the herd, the pasture must contain 180,000 square meters. What does 180,000 square meters? What measure is that? So the area, whoops, the area has to be, now what gave it away? Square, yeah. Square meters, that's an area. So the area has to be 180,000 square meters. No fence is required along the river. We'll assume that these cows, I guess it is, in the pasture aren't going to fall into the river. Okay, they're not going to cross the river. It's too much. They're not going to get swept away, so we don't care. I mean, they're just going to go down there and take a little bath. Okay, what dimensions will use the least amount of fencing? Let me ask this first of all. Can you reword that question in another way to use the words maximum or minimum? Can you use a word that can fit here? Go ahead, Addison. What's it going to be? Minimum. Minimum amount of fencing. That's another way of asking that question. I want to minimize the amount of fencing. Now,